Assalamu alaikum. We can use derivatives to find local extrema, that is, local minima or local maxima of a multivariate function. Let's see how we can do that. But first of all, we need to define the meaning of local extrema. So what do we exactly mean by local maximum or local minimum? Let's consider a simple function like this. So this horizontal axis means independent variables like x and y, and the vertical axis indicates the value of the function. Okay, so this point is a local minimum. That means if we pick this point and look around its neighbor, around this neighbor of this point, then this value has the minimum value compared to other points in the local in this neighbor. And similarly, this point is a local maximum because if we look around the neighbor of this point, so the neighbor of this point, there are no point that gives greater value than the value of this point. So that is the intuitive meaning of local minimum and local maximum. And of course, this point here is also another local minimum. But this may not be the global minimum because there is another point that that has a lower value than this value. So it's not a global minimum for sure, but still it is a local minimum because if you just look around the neighbor of this point, then there are no point that is that has lower values of the function. So let us give a more formal definition of local maximum and local minimum. First, suppose we have a function f of x and y on an open region U. And P is a point with coordinates a and b in this region. And first we define local maximum value. So we say f of AB is a local maximum value, local maximum value. So what this means is this. That is, if there is a delta that is positive, such that for all xy in the open region U, if let's say if x and y is in the delta neighbor of P, actually we require that to be intersection between delta neighbor of P and U, and xy is not equal to AB, then the value of f of xy is less than f of AB. Okay, so if this holds, then we say f of AB is a local maximum value. So what this means is that if we pick AB here, and if we have a delta neighbor, so if we pick small enough delta, and function is defined in this region U, open region U. So as long as xy is within this delta neighbor, actually intersection between delta neighbor and U, and xy is not exactly at AB, then the value of the function at this point is always less than the value of the function at AB. So that means within this neighbor, this value is the greatest, has the greatest value. So that is what we mean by local maximum. And the definition of a local minimum is similar, but we only reverse this inequality. So that is, we say f of AB is a local minimum value. So what we mean by this is the following. So there is a delta that is positive such that for all xy in the open region U, if xy is in the intersection between delta neighbor of AB and U, then the value of the function at xy is greater than the value of f at AB. So if this holds, then we say this is a local minimum value. Because in this neighbor, again, let's use this figure. So within this neighbor of AB, no value of the function is less than the value of the function at AB. So it is locally the minimum value as long as we stay in the delta neighbor of P. Now let's see how we may find local extreme values. So here's a theorem that is a necessary condition for extreme values. It's not sufficient. Necessary condition for extreme values. Okay, so as usual, let f of xy be defined on an open region U. And AB is a point in this region. And okay, suppose the first derivatives exist in this region. Then if f of AB is an extreme value that is either local maximum or local minimum, value, then the derivatives at this point, are 0. fxab is equal to fyab is equal to 0. Okay. By the way, local minimum or maximum values are collectively called extreme values. So that is, if we say f of AB is an extreme value, then we mean f of AB is a local maximum or local minimum. And we had a similar theorem for univariate functions, so we can use that to prove this theorem for bivariate function. So let's do it. So first of all, let's fix the value of y at b. Okay, so consider f of xb as a function of x, univariate function of x. Then we apply the corresponding theorem for univariate function. So if f of AB is an extreme value, then if we differentiate this function with respect to x, we have fx of ab. And differentiate and substitute x with a. Then this value should be 0. Okay, and we do this. Next, we fix the value of x and consider this as a function of y. And so similarly, we have fy of ab is equal to 0, and we are done. Very easy. But we should be careful that the converse of this theorem does not hold. This was also the case for univariate function. So even if we have these first derivatives equal to 0 at this point, it does not mean that the value of the function at this point is an extreme value. Okay, let's see an example. Consider this function f of x equals to x squared minus y squared. So if we differentiate this one with respect to x, we have 2x. And if we differentiate with respect to y, we have negative 2y. Okay, so at the origin, we have both 0, right? So fx of 0, 0 is equal to fy of 0, 0 is equal to 0. But if you look at this graph, so this is the graph of this function. So if you look at this plane where x is 0, not this one, like this one. So the graph looks like this. It's concave. So that is, let's see, if you put x equal to 0, then we have x0, y equals to negative y squared. So if we plot y versus f of xy at 0y, it looks like this. Okay, but if you put y equals to 0, then we look through this plane. So along this, if we cut this surface by this plane, it looks like, let's see. So the graph should look like this. Okay, so if we look at from this angle where x is equal to 0, the origin, it looks like to be a local maximum. But if you look from this direction, then it looks like this. So the origin is a local minimum. So actually it is neither local maximum nor local minimum. So even if we have both derivatives equal to 0, we don't have extreme values here. So this example shows that derivatives being equal to 0 is just a necessary condition, not sufficient condition for a function to have an extreme value. So how can we give sufficient conditions? And in the case of univariate functions, you may remember that we can use the second derivatives. In fact, in the case of multivariate functions, we can also use second derivatives, but it is a bit complicated because we have multiple second derivatives. Okay, here's the theorem. That's a criteria of extreme values. So let f of x, y be of class C2. That is, this function is at least twice continuously differentiable and on open region. So it should be defined on open region. And suppose the point AB is in this open region U, and the first derivatives at this point are 0. And let's define the determinant. D by the following. The second derivative fxx at AB times fyy AB minus fxy AB squared. Okay, so this is called a determinant for a reason. And then, first, if the determinant is positive, then in addition, if, maybe we should write a different letter, if fxx of AB is also positive, then f of x, y has a local minimum value. Value at AB. Okay. Instead, so if the determinant is positive, and if fxxab is negative, then fxy has a local maximum value. At AB. Okay, so if this is positive, then it's local minimum. If this is negative, then it is local maximum. Okay, and 2, if the determinant is negative, then f of xy does not have an extreme value. At AB. Now you should compare this with univariate functions. In the case of univariate functions, if we have first derivative equal to 0 and the second derivative positive at some point, then the function has a local minimum value at that point. And if the second derivative is negative, then in addition to the first derivative equal to 0, then the function has a local maximum at that point, right? But in case of bivariate function, since we have 3 different second derivatives, so it's a little bit complicated. So we define this thing called determinant, and if it's positive and this second derivative is positive, then it has minimum value. So this corresponds to the second derivative being positive for the case of univariate case. And if the determinant is positive and this fxx is negative, then the function has a maximum value. So this corresponds to the second derivative being negative for univariate case. Why this is so is is beyond the scope of this lecture, so I will not explain. And this is actually only applicable to bivariate functions. For more functions with many more variables, then we have different criteria, which I will not explain in this lecture because it requires more advanced knowledge about linear algebra, which I do not assume here. So just take this as a rule to decide whether a function value is a local extreme. Now, you should be wondering why this D is called a determinant. In fact, this is a determinant of some matrix. So this D can be written as this, fxx of AB and fyx of AB, fxy of AB, and fyy of AB. But since we are assuming that this function f is of class C2, this and this are identical. So if you so we can just replace this with fxy here. So if you calculate this determinant, then we have fxx ab times fyy ab time minus this time is this. So fxy ab squared. And this matrix, this 2 by 2 matrix for the case of a bivariate function, this matrix is called a Hessian matrix. It's called Hessian. And we can define a similar matrix for functions with more variables, like n variables. That will be n by n matrix. Okay, let's see an example. We consider this function shown in this graph. F of xy is x cubed plus y cubed minus 3 times x plus y. So if we plot this function, we have this graph. And let's try to find extreme values of this function. Okay, so first thing we do is to differentiate this function once. So let's see, if we differentiate with respect to x, we have 3x squared minus 3. Okay, so if xy is at an extreme value point, then this should be equal to 0. Okay, and similarly, if you differentiate with respect to y, that is 3y squared minus 3, this should be equal to 0. These are necessary conditions, not sufficient. But anyway, we solve these equations. So if we solve first one, we have so x squared minus 1 equal to 0, x minus 1, x plus 1 equal to 0. Therefore, x is either positive 1 or negative 1. And similarly, from 2, we have y equals to plus minus 1. So in combination, we have x, y equals to either positive 1, or negative 1, negative 1, or negative 1, positive 1, or positive 1, negative 1. So we have 4 possible points. So these are the candidates for extreme value points. But these are just necessary conditions, not sufficient conditions for extreme values. So in order to check whether they are indeed extreme values, extreme value points, we need to examine the second derivatives. Okay, so the second derivatives, fxx. So if you differentiate this one with respect to x, then we have 6x. And if we differentiate this, y, that is 0, because this doesn't contain any y. And fyy is 6y. And we calculate the determinant. Okay, so determinant is this times this, so that's 36xy minus this square, that is 0. Okay, so we check the sign of this determinant. Okay, so if xy is equal to this one, 1, 1, then the determinant is 36. That is positive. Okay, and what about fxx? So that is 6x, so x is 1, so that is 6. So therefore it is positive. So according to the theorem we have just proved, no, not proved, but presented, the value of f11, which is, so if we substitute 1 and 1, so that's 1, 1, 1 plus 1 is 2, negative 6, that's negative 4. So negative 4 is a local minimum value. Minimum value. So this function takes a local minimum value of negative 4 at 1, 1. Okay, now case 2. If xy is equal to negative 1 and negative 1, then d is equal to, again, 36. So that is positive. And what about the value of fxx? Negative 1, negative 1. That is, so again, so 6x. If we substitute x equal to negative 1, that's negative 6. That is negative, of course. Therefore, f negative 1, negative 1, that is, what is it? So that is negative 1, negative 1, and positive 6, that is positive 4, is a local maximum point, maximum value. Maximum value. Okay, next, if xy is, which one is first? Negative 1 and positive 1. Then the determinant is negative 36, which is negative, of course. See, negative 1 and positive 1, so that's negative 36. So that means the function value at this point is neither a local maximum nor a local minimum. Let's say, and the same thing happens if x is positive 1 or negative 1. So that's it. So that means when xy is 1, 1, then negative 4 is the local minimum value. When x is negative 1 and y is negative 1, then if the value of the function positive 4 is a local maximum value, and when x, y have different signs, then it's not an extreme value. So if you look at this figure, so x1, y1 correspond to somewhere here, somewhere here, I think. Then that should be the local minimum point. So when x is -1, -1, and y is -1, so somewhere here, that should be the local maximum point, maximum value. And when x is +1 and y is -1, so this one is not maximum or minimum. Because if we look from this direction, it looks like this. So it's concave. But if you look from this direction, it looks like this. It's convex. So this is such a point is called a saddle point. So it's not maximum or minimum. And same applies to -1 and 1 here, somewhere here. And that's it. See you later.